We're talking about wave motion, particles versus wave form itself. So we're considering a wave on a string moving to the right as shown below. What's the direction of the velocity of a particle at the point labeled A? Similar line of reasoning to part of one of the free response questions on either the 2017 or 18 AP exam. What's the direction of the velocity? This may have stumped you. At the moment of the picture, at point A on the medium, the oscillation of that particle is about to change directions. It's at its peak, at its maximum amplitude. So it's in the process of stopping and turning around to come back down again as the wave passes and the particle moves back towards equilibrium. So it's momentarily a velocity of 0 because the particle is at its maximum displacement. The follow-up is, what's the acceleration of the particle at point A? And that is that the acceleration is at its maximum. So it is 0 velocity, maximum displacement, but because it's as far away as it will get from equilibrium, it's at its maximum pullback towards equilibrium. So acceleration is maximum. Okay, so now consider a wave moving to the right as shown. Here's particle B on the wave medium itself. So particle B is this particle on the string. What's the direction of the velocity of the particle at the point labeled B? So you're considering that the wave is moving to the right. Is B at its peak, at its trough, somewhere in between? Where is it needing to move next as that wave shape goes to the right? So particle B is at equilibrium. As the wave form moves to the right, this place on the rope is going to start traveling up, 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 up until it reaches its peak, and then back down, 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 down. So B is at the point where its velocity is vertical, it's at equilibrium, so its amplitude is 0, its acceleration is 0, it's moving as fast as it ever gets, but there's no acceleration because it's not yet moving away from equilibrium, slowing as it reaches its peak to turn around. All right, so intensity has to do with the amplitude and the energy. They're kind of intertwined. So the particles in a medium travel, or the particles in the medium through which a wave passes vibrate in simple harmonic motion. And in simple harmonic motion, at least in terms of a mass on a spring, which we can model wave motion on a string as the total energy is equal to half times k times amplitude squared, where k is the spring constant of the spring attached to the mass. So we can say here then that energy is proportional to amplitude squared. So the energy held in the traveling wave is proportional to the amplitude of the wave squared. It's not that simple for things other than masses on springs, but at least to some level, we can model energy as being proportional to amplitude squared. So then we define intensity, not energy, but intensity. And intensity is defined as power per area. So the power delivered by the passing wave, which is energy per time, divided by the area over which the passing wave is spread. This is particularly important for 2- and 3-dimensional waves. The intensity is also proportional to the square of the amplitude, as we said above. So intensity is proportional to, or is equal to, power per area, and energy itself is proportional to area squared. So intensity is proportional to area squared. Amplitude squared divided by area. So if a wave is able to spread out in 3 dimensions from its source and the medium is uniform, then the wave must be spherical. There's no way for different parts of the wave to go faster than others. So we have these concentric spheres of sort of compression, or let's say peak traveling outward, followed by trough traveling outward, traveling by peak traveling outward, where they are spherical in nature because there's no point away from the source where one peak has exceeded the speed of any other of its peaks. So the amplitude is the distance each particle has oscillated from equilibrium, the maximum distance each particle has oscillated from equilibrium. The intensity is equal to power divided by area, the intensity is also proportional to amplitude squared, but we can also conclude then that the intensity decreases as 1 over r squared because the area of a sphere is 4 pi r squared. I think the take-home message here is that if you have a source that's causing a wave in 3 dimensions, the intensity, so the power per area, energy transferred per time per area, decreases as you get further away from the source. Oh, we can feel that if we're listening to music from a radio or from a speaker. As you get further away, the sound you hear decreases in strength. What is it that's decreasing? Well, it's the power per area. As that sound energy has to spread out over more and more space, energy is conserved and something has to give. And so its intensity decreases as 1 over r squared in a 3-dimensional setting. So intensity is proportional to the inverse square of distance. It's also proportional to amplitude squared. And so finally, we can conclude then that idea that the sound gets dimmer and dimmer as I get further away. The amplitude must be proportional then to the inverse of radius. As I go further away, the amplitude of the oscillation decreases until I get far enough away from the source of the sound and I don't hear it anymore. That's both an issue of the amplitude decreasing with distance, as shown here, but also that sound waves in air experience friction and they have an amplitude drop due to that friction, sound damping. But we're not going to worry about damping for AP Physics 1. Now, I do not think this is necessary to go through for AP Physics 1. What we want to consider is that energy is proportional to amplitude squared, as we discussed here, based on our model of a mass on a spring, and that intensity is defined as power per area, which allows us to make some conclusions about intensity and radius and how sound waves dissipate over space, not because of any kind of friction, but because of conservation of energy and the need for that energy to be sort of spread out over more and more space as the wave moves through space. The end.